Bayesian Hyperparameter Optimization. This is a technique that allows you to choose some sort of a loss function, so some sort of a function that you're trying to minimize, and there's a number of parameters, a defined number of parameters, maybe 5, maybe 10, maybe whatever, and you're trying to find the best options for that. Now, certain models, like gradient boosting, there's around 7 or so parameters that you need to tune for a gradient boosting machine, like the learning rate, gamma, other things like that. But it's just there's just a set number of them, like 7. Neural networks are a lot more complicated to optimize because there's a bunch of hyperparameters, and it's not a static number. It is structured. You might have 7 layers, you might have 14 layers, and each of those might have different numbers of neurons on them. So the fact that these layers in particularly are going to vary, and the number of layers is one hyperparameter you want to tune, this makes it kind of difficult to use your traditional optimization methods like Bayesian hyperparameter optimization on the neural networks, because that number of layers hyperparameter defines how many other hyperparameters you have. So we'll see how we can make use of these anyway. I have some links to read more about Bayesian hyperparameter optimization. We're going to load in a data set that we've used before. This is just a simple data set that has a combination of categorical and continuous values that you're going to attempt to learn the classification on. Now, what we're going to do is we're going to define 3 variables that we're going to try to optimize on. So these 3 variables, that's what the optimizer is going to try to find the optimal number of for the neural network. So dropout, this is easy. However many layers that we have, that is basically what dropout percent we're going to put on each layer. Neuron percent means of our maximum of 5,000 neurons, so I put in a limit. That is how many neurons all totaled we could ever use. What percent of those do we want to use? That basically puts it into a fixed range where I can put this value just between 0 and 1 because it's fundamentally a ratio. And the neuron shrink, I'm following the structure that I mentioned before, where you might have 500, then 400, then 300. You're kind of narrowing in. So this is the amount that each new layer will shrink based on the previous layer. Once we kind of run out, then that's the end. So that's the end of the pyramid, and that defines how many layers you're going to actually have in this neural network. So here I create a class of the neural network. I also load in into tensors the X and Y that we're going to be training on. But here you can see we're going to continue to shrink the neuron count by that neuron shrink ratio that we established before. That's one of the hyperparameters that we're tuning. And we're adding in a rectified linear unit and dropout on each of the layers. And we're going to do a maximum of 10 layers, and we're going to continue so long as whatever we started with, how many neurons, that hasn't shrunk to less than 25 neurons. You can see here I defined some values, and you can see the neural network that it created. It's very important, since this is PyTorch, you're going to have 47 inputs. That's just defined by our data. We're going to start out with 500. And then 500 to 125, 125 to 125. So you've got to always have that previous neuron count in there. Then we write this function that is going to actually evaluate the neural network. So you're being passed in the learning rate, the dropout, the neuron percent, and the neuron shrink. Those are the 4 hyperparameters that you're attempting to optimize in this error function. And this error function, the only way that it can work, and this is why it takes so long, is we've got to create a neural network and actually train it and see what we are able to train it to. And we're trying to just minimize that error from the neural network. So we're creating a neural network every iteration through training it, that takes some time, and then returning the score to the optimizer. And then the optimizer decides what the next set of hyperparameters, as it searches through this multi-dimensional space, trying to figure out what is the optimal set of hyperparameters for this neural network. And to do that, we are going to run through bootstrapping. We don't want to just train this once, because if we just train it once, we might have bad initial weights. So we're going to bootstrap split it through a number of times. We're not doing a whole lot here, but you could certainly put more onto that, and that would probably give you better results. I picked 2 just really to not have the processing time go too crazy. And then we create a new neural network according to these hyperparameters, the 3 that specify the neural network structure. The learning rate, that comes in when we actually set up the optimizer and train it. Then we train the neural network using early stopping, and at the end we evaluate it, and we're going to take a mean of the average. We're going to take the average of all of the runs that we've done. We just did 2 splits, so this would be the average just of 2, but you might want to put more in there to get a better result. We do put a negative in front of it just because we're trying to minimize, and that flips it around to a negative value. So you can see we can call the evaluation and with the 3 hyperparameters, and it returns an approximation of what that error rate is. If you want to know if you have enough splits going on, you can try running this multiple times and seeing how much variance you observe in the error that it's detecting. So now we're ready to hook it up to Bayesian optimization, and we're going to install the Bayesian optimizer. I say in Colab, because if you're running Colab, it doesn't have this installed by default. If you're running it on your local computer, this will also install it. And then we are going to go ahead and attempt to optimize it. We're specifying the parameters, the bounds for each of the parameters, because dropout, we don't want it to go too crazy. Dropouts above 50% are usually not useful. Too high learning rates are also usually not useful. So this is setting the ranges for each of these. We create a new Bayesian optimizer, and we're going to pass in that evaluate network. That's essentially the loss function that it's trying to minimize, and the bounds. We do track what the starting and ending time, because this does take a while. And you can see here, it ran here for about 12 minutes. You probably want to do more aggressive on splitting and some of these other things to really get a good result, but I was trying to keep it within reason in terms of output time. Then you can see here at the very, very end, it tells you what the best combination for those hyperparameters were. So this might be useful to you, some form of this in the Kaggle competition, if you are attempting to optimize hyperparameters, which usually in Kaggle you are. You probably want to do this more towards the end because it is computationally expensive, and you're going to be making all kinds of other changes to your model. If you change the structure of your model, then you invalidate a lot of this. Specifically, you evaluate the work that you've done here, because now if you change the structure of it, the optimizations that you did here probably will not apply. Thank you for watching this video, and if this was useful, please click the like button, subscribe so that you can see the rest of the course. Thank you for watching.